Okay, our next speaker after the break is Xiaobing Sheng. We'll be talking about divergent properties of different Thompson groups. So take it away.
Thank you very much. Thank you very much for the introduction, and thank you for inviting me here to speak. And thank you also for put the link in the chat, because my laptop is pretty old, so it's like I don't want to move around too much. So I actually emailed Alex saying that I'm going to talk about something new, but like it turned out that I don't have enough time to actually prepare for it. So I'm going to talk about this relatively old result, which is on archive, and then now it's also in chat. I'm going to start to introduce a little bit on the background and the motivation. And then I'll explain briefly the three terms in the title of my talk. And finally, I'll probably explain a little bit on the proof and also a bit on the future perspective of this project. So talking about the background, there are many Thompson's group experts here, but I'm still going to explain briefly, because I'm probably the first speaker to talk about Thompson's group. So these are the group, Thompson's group F, T, and V were first introduced by Richard Thompson in the 60s, while he was trying to find out groups with the unsolvable word problem. But these groups actually turned out to be to have solvable word problem. But they are really counterintuitive and interesting ones. And the two groups, the larger two groups, T and V, are actually the first two examples of finitely generated to infinite simple groups. And these groups have been generalized to an infinite series, first by Hickman and by Brown, by Sheng, from 70s to 80s probably. And then there are also many recent generalizations. But what I'm going to focus on today are just two generalizations, the Brown-Thompson group and braided Thompson groups. And many of the early results are on the algebraic properties and also topological and metric properties of these groups. But like the geometry of these groups are still very mysterious. It's also been mentioned in the previous talk that the geodesics of the groups are like, the quasi-geodesics of the groups are also mysterious. So like my personal interests are like hyperbolic type properties. We all know that Thompson's groups are not Gromov hyperbolic, but they might or might not have like hyperbolic type properties. This is actually this was the motivation that I wanted to start to look in on some geometric properties of these groups. So here I've listed some known geometric properties of Thompson's groups. So there are famous subgroup distortion properties, first being proved by brilliant. Sorry, it's a little bit small, so I'm like zooming in a little bit. Here are the groups embedded quasi-isometrically into Thompson's group. And then also some results on the generalization, especially on the Brown-Thompson's groups. And the three groups are distorted in Stein-Thompson's group and the higher dimensional ones. And there are also this really nice cat-zero cube complex that three groups are acting on properly, defined by Faraday, but the action is not geometric. So the three groups are really close of being cat-zero, but this has not yet been proved. And then there's also this Ding function results for Thompson's group F. The Ding function is quadratic, and for other T are polynomial. And last but not least, and this is far from complete, but like this is the main results that really motivated me to look at the geodesic scene generalizations of Thompson's groups. And there was this paper by Golan and Sapir in 2018, I think, on the linear divergence function of Thompson's group Ft and V. And there's also this preprint appeared last year by Kodama on the linear divergence of the braided Thompson's groups. So what I did was looking at the Brown-Thompson's groups and also other braided Thompson's group, and then prove that they also have like linear divergence. So I'm going to start from the first term appeared in my title of the talk, the divergence property. So the intuition is actually just we're looking at how two geodesics diverge from each other in the metric space. And this notion was first, this first appeared in the asymptotic invariance of infinite groups by Gromov, but first formally defined by Gersten. And then also like the notion appeared, bless you, in some other paper. And then there's also the generalized version, the relative version in Tran's paper. So here I'm adopting this formal definition here. So basically looking at 3 points in the metric space. And we're trying to find the shortest path between 2 points, which avoiding a ball centered at the other point. And then we are taking the maximum of all these. We basically want to find a linear path here, like in the context of Thompson's groups. We are just going to look at the Cayley graph of Thompson's group with respect to the standard finite generating set. So this is the notion of divergence function. And then I'm going to briefly introduce Thompson's group. So F is actually defined as the group of piecewise linear homomorphisms of unit interval from unit interval to itself with differentiable, which is differentiable at finitely many breakpoints, and all breakpoints are dyadic points, and all slopes are powers of 2. So this is one of the standard representation of an element in Thompson's group. We're basically picking up 2 unit intervals, and we have finitely many breakpoints, which are dyadic points, are dyadic rationals here. And then here for these 2 intervals, we have the same number of breakpoints. Then we have this piecewise linear functions, and these are all slopes of powers of 2. Like personally, I prefer to use another representation which is a pair of trees. We could actually correspond a binary tree to a dyadically divided interval, so that every breakpoint correspond to a caret, which is a graph with 1 vertex and 2 edges here. So these are the building block of a binary tree. Then we could use a pair of binary tree with the same number of leaves to represent an element of Thompson's group. But this is not really unique in the sense that we could actually add pair of carrots or delete pair of carrots, but they're not going to change the function, the piecewise linear function here. So for all those tree pairs, we quotient out some equivalence relation. So that represents an element of Thompson's group. And for every element, we actually have a uniquely reduced tree pair representation, which means that the number of carrots in each tree and the tree pair is minimum. And this notion can also be adopted to the other two groups. Like for T and V, we're just putting some variation on the labeling of the leaves here, because in the case of Thompson's group F, we are just mapping the first leaf to the first and then the second to the second. But in T and V, we have like cyclic and ordering and also permutations. So this is a rough definition of Thompson's group F. Now we generalize this to the Brown-Thompson's group. So here we're only changing this dyadic rational here to anadic rationals to be the breakpoint. And then using tree pair representation, we have to n-ary tree with the same number of leaves to represent an element in the Brown-Thompson's group. And also like these also follows for the T version, the V version also follows. So I'm going to say a few words about estimation of the word lengths using tree pairs. So the word length, we take in an element, it can be represented by letters in the finitely generating set of Thompson's group F. So in the case of F, this is actually the standard finite generating set we have. And the word length, there's a relationship between the word length and number of carrots representing the tree. And they're actually linear. So I should also mention, because Maurice here, there's this computational result. I only knew it like from a talk I heard recently. And there's this they're actually calculating the size of the tree and the number of carrots up to, like when you take a tree with really large tree of a really large size, then the number of carrots is actually roughly multiple, like some integer multiple of the word length. So this is in fact a really good estimation of the word length. And I need also to mention the support here. Thinking of the group element of Thompson's, the group element as the map from an interval to interval. And then the part that it changes is actually the support here. So we're going to use the notions for the proof, which I've written down the next slide here. So as I mentioned when I was talking about the divergence function here, we're actually going to find a path from a point in the Cayley graph to some other point and then avoid the ball. But here we're actually going to use Thompson's group F as a measurement for all other generalizations and all other larger groups. Here, the key here is to say for an example, or we're looking at an element from Thompson's group, say Thompson's group V. We want to find another element which is related to this element, and this element belongs to Thompson's group F. And then there's this path, which is a linear path, avoiding some ball centered at the identity element. So, and this path actually breaks out into 5 subpaths. The first subpath is to ensure that this element is large enough. I think this also has been reflected in Murray and other people's computational results, that if the size of the tree is small, then it's very likely to be reduced by adding or deleting, concatenating other letters. So this first subpath is to ensure that this first element has a large enough tree. Then the second subpath and fourth subpath are like standard geodesics in Thompson's group F. So like you can see they are formed by this conjugation. And they have like support which are disjoint. And the key is to look at the third path, because the fifth subpath is actually the inverse like of the first three and then the original one. So the third path we're taking here is a cyclic word, so that when concatenating this, the whole path is not reduced. And then we also wanted to avoid the ball. So it has to be like, it has the same size. It also has the same size as the original, the word length of the original element. And then we are going to use that key result here. So when we have two different elements in Thompson's group B, then we get to estimate, saying that two other elements related to these two elements, which is inside Thompson's group F. And then we could find two linear paths there. And there's also a linear path like connecting these two here, avoiding the ball. So which forms a large linear path. And this gives the linear divergence result. So now I'm going to briefly say a few words about the braided version. For the braided Thompson's group, this is why I like to use the tree pair representation here, because for the braided version, we're just putting the braids between the source tree and the target tree in the tree pair representation to represent an element. So there are like two versions of braided Thompson's group. One is actually generalized from Thompson's group F, and the other is from Thompson's group V. And by looking at the metro property, it's a bit more complicated, because the word length depends not only on the number of carets, but probably also on the crossings of the braids. So, but still, like we can also use the same trick using F as an estimate. So just take the larger group, BV, as an example. So it has 4 generators here. And we could see here, the first two are just the generators from the original Thompson's group F. and the other two are from the braided, braids. So the key here is, again, actually the third subpath here. Instead of the cyclic words, we are going to double the braid, or like make the braid as pure braid, so that because we don't want to have something called quasi element, which is like you're not changing the number of carats, but like your braid number, the crossing numbers are going to like be very, very large. So doubling the braid or making it as the pure braid, we could just keep the word length the same as the original one. And we could also just change the number of carats so that it's not like, it's not going to be reduced here. So this is the difference in dealing with braided version. And there are also two other braided version ones, which is like you have your leaves are like going to grow infinitely on the right, but like the method is more or less the same. We could use the same trick to just simply change this third subpath and double the braid. So I'm going to just say a few words about the similarity and difference, like my result, and also need to mention Kodama's result because I didn't know it like before I finished my preprint. So he was actually looking at the braid part and to make a graph like the braids in between two trees like this in order to like reduce the word length. But we are like both trying to shorten the path. And so I still have a minute. I'll just talk about like, I've been putting aside this project for a while. It is probably the right time like to start to think about it again. Because I think most Thompson-like groups, for most Thompson-like groups, you have like Thompson's group F inside. So like you can all use this trick to construct this path and then to prove the linear divergence. So it might be more effective to look at some relative version of the groups of the divergence properties. And also in the definition of chance, this divergence function is actually the lower relative divergence. So it might be more effective probably to look at some other notions. And there are also some other evidence actually really sort of reflected this limitation of looking at divergence functions. So I think there's probably much more to be explored. Yeah, that's more or less I want to talk about today, and I'm happy to taking any questions and comments.
Okay, let's thank the speaker.
Sorry.
Are there any questions for the speaker? If there are no questions, no questions. Okay. In that case, let's thank the speaker again.